I've been working on ARMX for a few years now. This talk is all about what it is, what my intentions were, and what I intend to do with it in the future. My name is Saumil Shah. I've been fantastically introduced like never before, so I'm going to skip this one. And let's just get on to what ARMX is. I've been playing around with embedded devices for a while, and I've also been teaching offensive security, exploit development, switched over from x86 to ARM-based systems because I needed to learn ARM-based systems, and what better way to learn than forcing yourself to teach it. Soon discovered that it's not very easy to put together a class which scales when there's quite a few students and everybody needs their own test system. So yes, 20 Raspberry Pis is kind of okay, but not very optimal. And a Raspberry Pi is not really representative of a typical IoT device. So my question was, how do I virtualize an IoT device? That's where the whole thought process started. When you're thinking about virtualizing anything other than x86, you always think about QEMU. So everybody starts with QEMU, and then you get all excited because QEMU can do anything. And then you read the documentations and you start this painful journey of suffering and excruciating intricacies with command line options and config files until a lot of time despair sets in and you just give it up. But I've been despairing over this for almost 4 years, and what I have now is something around QEMU, which I now call as an ARM firmware emulation framework. The word framework is very carefully chosen because frameworks never get finished. But it is released. The framework is out there already, and I very much intend to keep it going until it either graduates or something else happens to it. I don't know. The ultimate goal was to create an IoT VM. So that's my goal. I'm kind of not there yet, but what we have is something very close as you'll get to a device virtual machine. And why do we need to do this? Like, why don't we work on real devices? Well, sometimes a real device is hard to get. If it's like a blood transfusion system, you're not going to be able to play with those by buying it off Fry's or wherever you can. And it's just like, how many of these can you have? A few will get bricked. You need to have like a large lab supply of devices. So for most common tasks, virtualization is fairly convenient. Lets you do very good runtime analysis, static and dynamic stuff. You can reverse engineer it, load your own tools on it, fuzz it, exploits. And now I'm told it's also very good for running CTFs on devices. Actually, a few of them are starting to use ARMX for CTFs. And what I gained out of this was like some fantastic insight on embedded hardware by trying to emulate it. You have to learn it yourself. So I'm going to give you a demo of ARMX, but I'm just going to first give you a tour of the system, what it does. And then we'll do some demos and end the talk with question and answers. So ARMX is released as source on GitHub, and I also created a preview virtual machine which you can download and play. Looks something like this. When you start up ARMX, you get a nice menu. Every device that's emulated appears as a menu item. You can add your own devices, provided you have the firmware for it, you have the kernel for it, you have the config settings for it. And I'll take you to a tour of this. But before we get into understanding how each of these devices works, let's first look inside what a device is. It's typically any connected system internally is quite similar to what you're used to in the desktop computing environment, but slightly different. You, of course, have your native CPU and hardware. It's all implemented as a system on chip. The file system, kernel, all these things live in firmware. They don't live on spinning disk. And then you have your user land processes, system services, custom applications, exposes a user interface, and whatever functionality it provides. This is typically how everything looks like. There are several little differences between a desktop environment or a block-based computing environment and an IoT device, in the sense that there's no persistent storage as you might find on a typical disk. You can read and write to a disk, but here on devices, everything is in flash memory. More or less, it's read or flash. You can't like write individual stuff. All your persistence typically happens through what's called non-volatile RAM. You have a section of flash memory which you can write to, but it's small, it's tiny, and it only stores the most essential setting. I mean, this is what you can typically find in your routers, or your IP cameras, or your IP phones, or whatever device that you're using. So what happens when you power up? Let's say, for example, you power up a router. First, CPU gets powered up. It finds where the firmware is. The firmware exists in flash memory, like giving you a very simplistic overview of things. And the CPU goes and looks for where the bootloader is, transfers control to the bootloader. The bootloader kicks in. The bootloader is configured where to find the kernel in the flash memory. It finds the kernel. Now, the kernel kicks in, and it needs to find where the file system is. Now, this is where some of the fundamental differences begin. File systems, they don't live as like blocks and inodes on a disk. On a device, everything, space is a big premium, so everything is compressed. And your file system is also compressed. It either exists as a squash FS or a cram FS or something like that. The kernel then uncompresses the file system as a RAM disk and mounts everything in RAM. Everything that happens above this layer is all in memory. There's nothing persisting on storage. And eventually, the kernel transfers control to user land. The user land is a very messy affair on IoT devices. It basically consists of a spaghetti of startup scripts, something that initializes your hardware subsystems, your networks, your USB devices, your blinky lights on the router, all those things. So you see like these weird messages go up. Some of them are even generating errors. But every vendor has implemented their own custom startup code. And once these scripts start up, what they do is they end up pulling variables from NVRAM, stuff like your IP address, your password, your DNS server, network share. All these configuration details are stored in NVRAM. They get pulled up, and all your device configuration files are written on the fly. So all your configs are built up in RAM disk every time you power up. Stuff like network config, DNS mask, Samba config, Wi-Fi supplicants. All these are written on the fly by these clumsy scripts. And then it is time for your services to start. So then HTTPD starts, Samba services start, video driver starts, whatever you may have. And on top of this, you have your applications, and then the device is booted up, and it's ready. When we're dealing with something like this, the question is, how do we go about emulating this process? There are a few goals that I needed to match. I wanted to keep the emulation as faithful to the actual device as possible. Emulating IoT devices is not unknown. Several people have tried to do that before in several different ways. The most simplistic approach is to emulate a single binary. Like you want to test a web server on a router, you can use a QEMU user environment. Just load an ARM binary in your regular x86 environment, emulate it, you can test it. You can get pretty lucky with that, except when you try to exploit it on real hardware, things may be very different. Your offsets will be different, assumptions will be different, the CPU architecture will be different. Most of these attacks won't work outside of your QEMU environment when you try on a regular hardware. So my goal was I should keep this as faithful to the regular hardware as possible, which means I need to emulate the CPU as closely as possible, the kernel as best as possible, and then not try to fake the userland environment, but literally try to boot the entire userland code in the emulated environment as is, without making a single change. So the next slide, I'll just outline some of the goals and challenges with the emulation approach, and then we'll see how I did this. Instead of the CPU, I'm now going to use a QEMU environment with a matching QEMU board. Currently, the emulation exists only for ARM devices. I've got ARM v5, ARM v6, and ARM v7 emulated. I'm working on MIPS and other such devices, but that's going to be like probably early next year. NVRAM was a big bottleneck. There was no clear documentation on how to emulate NVRAM until I finally got it going through some custom build root stuff, which was pretty nice to do. So far, NVRAM has been emulated by hooking it. You essentially patch libnvram, you insert an LD preload hook, intercept the functions, and fake it through an ini file. There's, I think, Zach Cutlip's project on it, and a few others have successfully done NVRAM emulation. NVRAM interception. I instead shortcutted the whole thing out and let the device use its native libnvram and just pull it out as if it's really interacting with an NVRAM device. Shared memory comes to rescue over here, which was a neat little thing. So for me, the emulation challenges were to try and emulate as much of the hardware as possible. Sometimes I can't emulate all the hardware. Like if I'm doing an IP camera, I don't have a frame buffer, so I don't have a video device. All your video I/O will be blank, but everything else will be working. So I can test the file sharing subsystem, I can test the admin interface, I can test all the streaming protocols. I just can't test the video driver. So you're not going to get 100% equal to the actual device, but as close as possible. So some of the drivers may fail, some of the devices may fail, but the rest of the stuff will work. As far as the firmware goes, I can extract the firmware from the device. I can also get it from several other sources. But I cannot use the kernel that I extract from the device directly. This is because the kernel is built for a certain type of a circuit board, which does not necessarily match with QEMU. So one of the current bypasses that I've got going on is I just recompile the same kernel as far as possible with the same version and get equal to the kernel config that is present on the device, either by trial and error, or sometimes I get lucky if I get procconfig.gz, I get all the config parameters and I just build the kernel the way it is. And once you have a matching kernel that works on QEMU, it can run the entire userland portion of the device as is. So I want the kernel to match with the CPU architecture, and as far as possible, all the config settings. Then comes the file system. The file system on the device exists in a compressed format. What I do is I just uncompress the file system and leave it in a normal workable state. Because during testing, I want to manipulate this file system fairly easily. I want to be able to add my own tools. I want to be able to modify things on the fly. I don't need to reflash it every time. So sometimes I also need to look through the default configuration files on the file system where the factory settings are stored. And I need to tweak some of these configs to match the QEMU environment, especially for IP addresses and default interfaces and such. Eventually, I also want the emulated device to be able to be network reachable, so you can fuzz it remotely, attack it remotely, all sorts of fun stuff. The entire userland emulation happens in a chroot environment, which runs on top of the kernel. So then once you get, you have to do a lot of troubleshooting for this. Once you get a new device, be prepared to spend about a week of trial and error looking through all the scripts and trying to duct tape little things as far as possible. Until after a week or so of immense frustration, you'll finally get that golden light and the UI will pop up and things will actually start working and behaving. And this is where you can actually now start testing and playing with the device. So some of it will work. Like over here, if you try and look at the video stream, you'll just get X's in there. Some of the components are just not emulated. I mean, we can play with video for Linux drivers and fake those as well, but that's like an ongoing process. I don't have that ready yet. How does the whole thing come together? Let me give you a quick tour of ARMX. It's a wrapper around QEMU. There's a main shared directory called ARMX, which hosts all the device definitions, the templates, the configurations, and the firmware extracted images in this entire tree. This directory is available on the host, as well as it is shared using NFS inside the QEMU guest as well. The QEMU guest will boot up the custom kernel, which is populated for the device. The matching kernel is booted up. The guest will first boot up its own default file system, which is standard, which has all the tools and scripts to launch other things on it. And this is generated by build root. It has a tap interface. The host is always hard-coded to 100.1. The guest is 100.2. I mean, these are configurable, but at some point I'll make it nice and editable. And once this QEMU guest is booted up into its default file system, it mounts the entire ARMX tree using NFS and then selects the root file system of the extracted device and boots it up from within. There's a lot more details on the web page. So I know it's a little confusing. It was confusing for me as I was drawing these diagrams. I got lost myself. The entire thing, I've just tried to keep it as simple as possible. Everything is a nice hierarchical directory tree. The main database is called devices, where you can create and add your own devices. These are some scripts which just stay static in the run directory. The host file system is also fixed. You just generate it once and let it live. That has all the tools for the userland stuff. And then all your new devices will be created under its own template. You can copy a template and just create a device. Each device has its own config, its own copy of NVRAM, which gets populated before the device boots up, a kernel, which is generated using build root, and the root file system, which is extracted straight from the device. How does this all work? Well, first, you have a launcher. The launcher will parse the device database, give you a menu, and let you choose which one you want to boot up. Then, once you've selected what you want to boot up, the launcher will then boot the kernel inside QEMU. This is the matching kernel that has been generated for the device. The kernel will then activate the tap interfaces and load the host file system and get ready to launch the userland scripts. The userland scripts are available on the NFS share, so that share gets automatically mounted under the same directory path. Actually, NFS was a big lifesaver. I was really struggling to figure out how to share stuff between host and QEMU guest, and then old Solaris NFS comes to the rescue. NFS is never going to die. It's beautiful. Highly vulnerable too, but that's a different story. So once the QEMU boots up, you get a console with the kernel and the host FS booted up, and it looks something like this. And at this point, the kernel is ready, host file system is mounted, the NFS tree is mounted, and now we're ready to kick off the userland scripts. How does the userland stuff work? So for that, you just log in to the host FS. You can SSH in, and by default, you'll get a menu. It allows you to do two things: either boot the userland portion of the device, or you can get dropped into a debug shell if you want to do something before booting up the userland scripts. When you boot up the scripts, these are all the scripts that are from the extracted file system of the device. The default init scripts, you just tell the shell which script to kick off, and the scripts will kick off. You may have to spend some time duct taping some of these scripts together. For example, in the IP camera, it looks for a hard-coded /dev/video device, and this device doesn't exist. So you just fake it using a touch command, touch a device. It'll complain, but it'll somehow go through. You just want to push the cart through until it loads everything. And once it loads up, then you can play with it. So a little bit of R&D is required for this phase. Once you get it all down, you can script it up and define it in the config. And then the init scripts will run, all the NVRAM stuff will work as is, config files get created, and eventually when the device boots up, you actually get a shell on the emulated device, as if it's a real emulated device. All the init scripts have run, all the applications are running, and now if you connect using a browser, you'll be able to play with the device in its entirety. So this is the demo I'm going to give you. I'm also going to show you what the debug shell does. The debug shell is interesting because once you boot up the device, you want to obviously test it. You want to fuzz it, you want to debug it, you want to break it. So the debug shell hosts a lot of utilities. You get your usual GDB server. You also get ltrace, strace, and any other utility that you want to throw on. That's all a part of the host FS in the build root. These tools are already preloaded. So you can now launch a debug shell, attach a GDB server to a process running in this IoT environment, and remotely launch a GDB, connect to the remote GDB server, debug it, crash it, play with it, fuzz it, whatever you want to do. So let's see a demo. Let me show you how this whole thing works. Then we'll talk about how to add a new device to it, give you another tour of firmware, and everything's good. Okay. So here's ARMX. This is just a default desktop. You get an icon to click. It'll give you this nice little menu. And you can select which device you want to load up. All these devices are listed in the device database. The device database is over here. This just exists as a little text file. And each line is a device definition. All this gobbledygook is QEMU stuff. So for example, the IP camera, which is the last one defined, you need to emulate it using a versatile prototype board, which is the default board for ARM v5 chips in QEMU. You find that out using much pain and suffering. And then you figure out how much RAM you want to give. Here's the kernel image, the Z image 263 for the versatile board. And I also discovered that this kernel does not like thumb binaries. So I have compiled it without thumb binaries to match the actual IP camera. All this happens using build root and custom kernel stuff. These are the storage interfaces for QEMU. It fakes an SD card, and all the images, the file system appears as a fake SD card. These are some of the boot arguments. So this is where your console is bound to the serial port. I just left it as is from the actual device. You emulate a network interface card, and this is the descriptive text. So each entry in this device corresponds to one emulated environment. Let me show you what exists in there. Each device gets its own directory. The host FS, by the way, is always just one. There's only one host FS, and there's an ext2 file which has all the tools. All the scripts are in the run directory. Let me go to the device directory though. The device directory always has 4 or 5 components. The default file is a config file. Config is rather simple. Tells you what device ID it is, whether it uses NVRAM or not. This IP camera doesn't use NVRAM. Where the root file system is extracted, that's in the root FS directory. The kernel, the Z image, lives over here. Whether you want ASLR on or off. And these are the init commands. These are the commands to invoke when the kernel is booted up. So what should the userland scripts be? This is where I was telling you I'm faking the video device. I'm just doing a touch command, creating a fake video driver, and then init, rc.sysinit, rcinit3, and then drop a shell. And then there are some helper scripts like run init Run in it always remains the same. It loads the config file, it loads NVRAM if there is any, and then it runs the userland scripts in a chrooted environment. The kernel, it's just one Z image. You compile it in build root, drop it over here with all the configs. Rootfs, here are all the extracted files from the compressed file system on the device. So this contains all the binaries, all the device trees, everything over here. All the applications are in this environment, and this lives in its own directory. Let me show you what happens when you start it. So when you start it, here it goes, compresses the kernel, boots it up, and then drops you into this ARMX prompt. At this point, the kernel is booted, the host FS is loaded, and now we can try and get into the shell. Shell is one click away. You basically get either a default bin shell, which is the debug shell, or you can go and start the userland scripts. When you start the userland scripts, it loads the NVRAM. Here there's no NVRAM, and it waits to oops, I started actually. Did I start the IP camera or what? No, I didn't. My error. I want to start an IP camera. Kill everything. Okay. Sorry. Yeah, I started the tiny exploit first, which I was not intending to do. I want to start this guy. Much better. I was wondering why is it looking different. Well, you can see it's very easy to just shut one off and turn another on at will. And that makes for a lot of flexibility. Let's start the IP cam. Now here are the init scripts running. You can also see some errors being thrown on the consoles, like some drivers are failing, but that's okay. We just have to be brave and suffer these errors. Right? And at this point, all your applications are running. If you actually do a PS on your prompt, all your you have a web server running, you have storage drivers running, HTTP client, the video streaming servers, some IP cam daemons. And at this juncture, you can actually pop open a browser and pull up the web interface of the IP camera. This lets you do everything that the regular IP camera does, except it doesn't show you a video. But you can play with settings, network settings. At this point, if you use Burp Suite, you can fuzz this web interface. You can find all sorts of web hacking bugs, directory traversal bugs. Go for it. The device is ready for attack, exploration, exploitation, whatever it is you may have. And it'll react to all your normal interactions. Okay. Let me show you the debug shell. Here's the debug shell. The debug shell lets you interact with processes, and you can attach GDB server to, say, a running process. Let me attach to the web server process, which is this one over here called webs. Okay. Yeah. And the GDB server is attached. And now I can remotely debug this guy. I can attach a GDB. And the GDB server is attached. I've got my GDB prompt. I can look at the binaries that are loaded or the virtual memory map. And I can play with this. I can now fuzz it or test it. And well, yeah, let's see what we can do with it. Let me get back to the slides, discuss some more about the devices, and then we'll do a little demo, wrap up. So what you just saw was this whole thing in motion. The kernel is over here. This gets loaded up. So if you want to create a new device, you got to create a new template. The config files and some NVRAM files will already be present, so you can use those straight away. You need to obtain three things. First, you need to get the kernel. The kernel you compile yourself using build root. Then you need to get the root file system and a copy of the NVRAM if it is needed. The way you obtain these are by firmware extraction. And there's three ways you can extract firmware. The first and the easiest way is look up the manufacturer's website. You usually get a CD-ROM. Well, these days, who has CD-ROMs anyways? But you get a bin file. You grab the bin file. You at least get the file system. You won't get the NVRAM, though. The NVRAM is only available at runtime. But at least you'll get the root file system, and you can start playing with this. The second and the more preferred way is by getting a serial console onto the device. You run the risk of bricking the device, but it's worth doing it. So you go open it up. You find where the UART is, if there is one. And sometimes the manufacturer leaves the shell available on the UART. You figure out where the pins are. You solder them. Hopefully, the manufacturer hasn't broken some of the tracks, and you'll get a serial console. If you get a serial console, that's great. Either you have to brute force the password, or you luckily get dropped into a root shell. In that case, you can simply dump the firmware using DD and just dump the MTD blocks. These are the partitions, and extract them. You can get the U-boot, you can get the kernel, NVRAM, root file system, whatever you may have. This technique works rather well on several devices. Now, if the device does not expose a serial interface, or if they've broken the tracks or something, the only other way is you have to take it directly from the chip. You clip something on the flash memory and suck it out right off the chip. There are some janky ways of doing it. You can use a bus pirate, or if you're Joe Fitzpatrick, you can simply whisper to the chip, and it'll give you all the bits. Fitz can do that. I am not the Fitz. So if you really want to do it, the best $200 you'll spend is on this thing called the A6 Forte. It's the Rolls-Royce of chip suckers. It's as close as you'll get into like clicking it, defining what chip it is, pressing a button, 15 seconds, the image is extracted. It's really, really good. Be sure to wire these things correctly, otherwise something will burn, either your device or the Forte, or both. And you don't want that happening. So, but it works. It works really well. So I'll give you some demos of an exploit on the IP cam, and then that should bring us to wrapping it up. Okay. So here we go. The debugger is working, and well, there's some vulnerabilities in the IP cam, of course. There have to be. By the way, you can download this preview VM. It's available online already at armex.exploitlab.net. The addresses are in the slides. And the VM comes ready with this IP cam for you to play with. It's not a fake image. It's a real device emulated. I've opened it up as a CTF. If you manage to crack this, there's a special deck of cards, which I will give you as a prize. It's, yeah, just mail in the results. OK. So, oh, that's awesome. I'm going to announce it. I'm going to tweet that. OK. Exploitlab.net. Yeah. It's there. It's in the slides, and I will be publishing it. OK, where was I? That countermeasure freebie got me all off balance. I'm very giddy now. I have to have some water. OK, IP cam. So there's some There's some exploit scripts. I mean, I've tested this device. I know where the bugs are. There's a nice little info leak on here, which is kind of interesting. Let me show the info leak. It's a format string bug found by fuzzing. You info leak it, you get all these addresses, you get some library addresses and stack addresses, everything leaked out. I initially used the info leak because the web server on this device is a single-threaded server, so you can't attack it repeatedly, you can't brute force it. And I thought, like, damn, if ASLR is running on the device, we need to info leak it to be able to get a stable attack going. Well, it turns out that every time I booted the device on the actual hardware, it gave me the same addresses. Then I bought another IP camera, same addresses. And there is no ASLR. Like at that kernel level, 2.6.28, it did not do ASLR. So this whole bug was wasted. Like 3 days in finding an info leak, only never to use it. Here's the actual bug. There's actually 2 bugs. This one was submitted by my student, which is a much better bug than I found. You, of course, send it a very large URL of all sorts. Several CGI parameters are vulnerable. Like this big block of A's will essentially cause a stack overflow. And when we hit it against the actual device, you'll actually see the crash occur in the debugger. And you get this nice array of 41, 41, 41, 40. You control your program counter, and this crash is beautifully exploitable. Once you get this going, I need to restart the web server on here. I can do that rather easily from the shell. Restart it. I, of course, have a full working exploit for this as well, which I'll show you. It launches a reverse shell back to me. And this is pretty much the exploit. So the base address is your reverse shell shellcode and usual stuff, right? And I hit it against target. If all goes well, we have a shell. Shells always get the claps, man. Yeah. And you can see here's a CPU is an ARM v5 CPU. It's pretty much the same as what you find on the actual IP cam. I forgot to bring my IP cam with me, otherwise I would show you the same exploit working on the IP cam. If you find a used model of this TriVision cam on eBay, try it. The same exploit works. Not only on TriVision, it works on UCam, it works on like 5 different brands of vendors. They all use the same OEM software, just change the logos. And they have no intentions of fixing these bugs. So this is a shell. Right. What else do we have time for? That is a little bit of the demo. I'm forgetting something else I wanted to show. Oh yeah, let me show you another router which uses NVRAM, for example. This one was a very simplistic one. Let's see a more complex device. I'm not going to be able to show exploits for that or anything, but at least let me show you how this works. So I'm going to stop this one. And we'll see a more complex device like the Netgear router. The Netgear is a pain to emulate. Netgear uses everything in NVRAM. And getting this going was a huge challenge. Exploiting this was also a pain. But you boot up the Netgear router, the kernel. I'll show you the NVRAM contents of it. The config file for the Netgear router is defined like this. So all the NVRAM contents are in this nvram.ini. The root file system is in rootfs, and some libraries I have to inject because otherwise the Nighthawk tools don't run. This is the nvram ini file. You can see all the usernames, passwords, backdoor Netgear passwords, everything in here. By the way, the default password to any Netgear device is gear guy and gear dog. These are built in. And that you find out when you extract the firmware from the chip. This is all in here. It's good stuff. Maintenance mode, man. There's a reason for that. Okay, let's start the Netgear router. When you click it, it first loads all the NVRAM into the shared memory. So this populates the dev NVRAM device, which the kernel will then use, and the router will then pick up all the NVRAM settings from here. It takes a few seconds to load. I'm just trying to have some optimization to do it faster. This is as fast as I can get it going. There's a lot of NVRAM entries though. And once these NVRAM entries are loaded, you'll get a prompt which says press enter to start. You press enter, you now see all sorts of error messages start popping up on these devices, on the console, and sometimes you'll also see them on the shell environment. It takes a while to get it going. I think by now it is started up. And sure enough, here you go. This is the actual Netgear router. It even uses all the settings from the NVRAM dynamically. And it functions just like a normal Netgear router. You can exploit it and do whatever you want with it. So even for complex devices, ARMX works rather well. Okay. Future directions. So I'm trying to automate some of the debugging tools. I'm going to try and put some fuzzers into it, especially work on the host FS region for analysis, static and dynamic. All the goods. These are the URLs, armx.exploitlab.net. I'll be announcing all new updates on my Twitter account, should you wish to follow me. My account is the real Saumil. And if you want to take the IP camera CTF challenge, there's a blog post up on blog.exploitlab.net. With that, I conclude my talk.